according to Charles's law, a volume of gas will expand and contract based on the change in temperature. He says that volume and temperature are correlated with one another as long as pressure is held constant. So, if we increase the temperature of a gas, the volume should also increase. If we decrease the temperature of a gas, the volume should subsequently decrease. So the goal for this lab is to take 5 different beakers, make water baths at different temperatures. So I want to go from -15 to -10, approximately 0, 20 degrees, somewhere between 40 and 50 degrees, and then 80 degrees. And I want to take a sample of gas. I'm just going to use air, and I'm going to trap it in a gas syringe that has a plunger that can move. And so when the gas contracts, the plunger will decrease the volume, or the volume will decrease as indicated by the plunger. And if the temperature increases, the gas should expand as indicated by the plunger. And so when we're reading a plunger, we want to make sure that we're reading the part of the rubber gasket where we see the edge of the gas. And so we don't want to be using this part of it. We want to be using it where the gas is held, this first black band, okay? And then we're measuring in milliliters. So every line is going to be 1 milliliter. So to start off with, I've already trapped 30 milliliters of gas in my syringe. I'm going to make my baths. The first one is my super cold one, and so that's going to be between -10 and -15. To prevent it from freezing, because water freezes at 0 degrees Celsius, I need to add some salt to the beaker first. And so what the salt does is it will lower the point in which the water will freeze. This is called freezing point depression. So I'm adding the salt. Okay. And then I'm going to add some cold water to this. And lastly, I'm going to add some ice. Daniel Fahrenheit established the Fahrenheit scale, the temperature scale, based on the premise of the coldest temperature you could achieve in lab would be the 0 value. And so if you combine equal portions of salt, ice, and water, and you mix it thoroughly and continuously, it should achieve a temperature of 0 degrees Celsius, or 0 degrees Fahrenheit, which corresponds to roughly -17 degrees Celsius, 17.7 I think it is. And so we're not going to be able to get that cold in lab because it has to be continuously stirred, and we're not going to be able to do that. And we would also need a better ratio of salt, water, and ice, but we should be able to get below -10 degrees Celsius. Okay. So while that's getting cold, I'm going to prepare my next bath, which is going to be approximately 0 degrees Celsius. And so I'm going to add some water, cold water, and then I'm going to add ice to that one as well. So this one is different than the first one because it does not have salt. And I have a couple more ice cubes. I can split between them. So this one's going to get colder because it has the salt, and we're decreasing the freezing point. So freezing point depression. This one is just going to be normal ice water, and so it should achieve the temperature of the melting point of ice, since we're going to have solid ice and liquid ice in the same system. So this one hopefully will get below 10 degrees, and then this, or below -10 degrees, and then this one should approximately reach 0 degrees Celsius. So we have -10, 0, and then this next one, we want it to be room temperature. And so I'm going to add about half cold, half warm to accomplish this. And I'm going to hope that I get roughly 20 degrees Celsius. The next one, this is going to be the warmer one. So this is somewhere between 40 and 50 degrees Celsius. To achieve this one, I'm going to just run hot water. I'm going to wait for the water to start steaming out of the spigot. And once that's the case, I will then take the water in the beaker. The intensity threshold for water, so the temperature, is 54 degrees Celsius. So that's the point in which you will start to burn yourself if you touch water that's 54 degrees Celsius or hotter. So I want this, well, I could approximate the temperature to be roughly 50 degrees Celsius if it's not burning me if I stick my finger in it. Okay, and so that's not super hot. I can tell that it's hot, but it's not painful. So that's going to be somewhere between 40 and 50 degrees Celsius. And then The last one, this is the one that I want to be hot. I'm going to heat this to 80 degrees Celsius, which is far above the 54 that can burn me, so this is definitely going to be hot. Remember, the boiling temperature of water is going to be 100. Okay, so I'm going to put that on the hot plate. And so now that I have my isolated gas, so it's starting off at 30 degrees, 30 milliliters at room temperature, I'm going to put it into the cold one, the coldest one at -10 approximately, and then the next one at 0, the next one at a little bit below room temperature, probably around 20, the next one 40 to 50, and then the next one 80. Okay, and we're going to get measurements for the volume, as well as we're going to measure the exact temperature for each one. Okay, so for the temperature of the salt, ice, and water, we'll let the temperature acclimate, and then we'll record the temperature. And then we will put the gas in there, and we'll let that acclimate. It should take about 2 minutes, okay? But since this is a virtual lab, we can kind of cheat. So we're going to take the volume measurement now. We'll take that out. We'll take the temperature of the ice bath. Now we'll take the volume of the ice bath, or the volume of the gas in the ice bath. Now we'll take the temperature of the room temperature one, roughly 20 degrees Celsius. I'll determine the volume of the gas in the room temperature one. Again, we're cheating, but it's going to change volume. Here is the temperature of the one that's between 40 and 50. Record the temperature. Let the volume of gas acclimate in the water. Wait 2 minutes and read the volume off the side. And lastly, I'm going to take the temperature of the one that's just below boiling at roughly 80 degrees Celsius. Read the temperature. Then I'm going to put the gas in there, wait 2 minutes for it to acclimate, and read the volume. What we have found is that the volume of gas was lower when it was cooler, and it was greater when it was warmer. And so by being able to graph that data, we should be able to extrapolate our data to even colder temperatures and see exactly what happens with the volume of the gas.